Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module Sputtering Techniques from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we are going to learn about the underlying principle of sputtering deposition technique. Then we'll study in detail about the mechanism of sputtering technique. Then in the next section, we will see the different types of sputtering, that is radio frequency, that is RF, direct current or DC, and magnetron sputtering. Then we'll see the difference between DC and RF sputtering. Then in the last section, we will study about the RF diode sputtering and the RF magnetron sputtering, the comparison of the two types of sputtering. So to start with, let us have a brief introduction about what is a sputtering technique. Sputtering technique or the cathodic sputtering was discovered by English physicist W.R. Groove in 1852 and developed as a thin film deposition technique by Irwin Langmuir in 1920. In order to produce stoichiometric thin films, that is, without changing the composition of original material from target, material sputtering technique or a high energy fabrication method is utilized. Sputtering is also effective in producing non-porous compact films. This technique is an efficient tool to deposit multi-layer films for mirrors or magnetic films for spintronics, that is, the devices using spin of electron and hole along with the charge on them applications. Sputtering. In the sputtering technique, atoms from a solid target source are ejected or sputtered via a process of momentum exchange inside the plasma by the action of high energy ions, usually originating from some inert gas ambient like argon. The ejected particles are then deposited or condensed on the surface of a substrate to produce a thin film. Now, what is a plasma? Plasma word is taken from Greek plasian, meaning to mold or to spread. Plasma is an ionized gas that is considered to be a distinct phase of matter. Plasma is electrically conductive and is strongly influenced by electric and magnetic fields. Plasma is an ionized state of matter containing ions, electrons, and neutral species. Plasma is used to derive ionization, creating a large number of ions and free electrons. Plasma is generated by applying DC or AC voltages, and a bias voltage is applied to the target to promote acceleration of ions. Sputtering mechanism. Ions of the inert gas like argon bombards the target surface at a very high energy. The ion-target interaction can be a complex phenomena, that is, the kinetic energy of the impinging particle largely dictates what event would take place. So depending on the energy of ions and the ratio of ion mass to that of target mass, the interaction of ions with the target material is dependent on the
energy of the colliding ions. The incident ions may get bounced back when their energy is very low, that is less than 5 electron volt. Whereas for energy greater than 10 kilo electron volt, the collision is nearly head on and they get embedded in the target material, which is the basis of actual ion implantation. A number of interaction mechanisms are possible depending on the value of kinetic energy. That is, if it lies in the range of the above two extremes, that is as low as 5 electron volt or as greater as 10 kilo electron volt, then its collision cascades can be created in target atoms. Vacancies can be created displacing some of the atoms in the target, interstitials, and other displacing acts. Absorbates are desorbed, photons are created while losing energy to target atoms and sputter out some target atoms, molecules, clusters, ions and secondary electrons. For the deposition of materials, one is interested in the sputtering yield. Sputtering yield is defined as the number of ejected species per incident ion and increases with the energy and mass of the bombarding ions. Sputter yield for different elements with same incident ion having same energy varies in general. Therefore, in case of a target consisting of more than two different elements, the one element having a higher sputter yield is incorporated in large amount than the other element present. But the material with high sputter yield also gets depleted at a faster rate and other elements present thus make a higher contribution in total. Henceforth, the required stoichiometry is achieved in the deposited thin film. So, sputter yield is the important parameter for the deposition of materials. The figure given here shows the interaction of an ion with target, or the given figure shows the mechanism of sputtering that we have discussed in the previous slides. In the given figure, we can see the absorbed species, then the energetic particles, some enhanced chemical reactions, photons which are ejecting out, the secondary electrons which are ejected, and the sputtered atoms or ions that are being given out. We can also see the lattice defects which are caused by trapping or the particles which are implanted, displaced. So, this figure gives the gist of the mechanism of sputtering technique. For the highest sputter yield, a following set of conditions are valid. Number 1, process gas should be of high atomic weight. Number 2, cathode material should be of low atomic weight. Number 3, amount of reactive gas species should be low in the vessel. The most commonly employed process gas includes argon in the sputter deposition processes because for most metals, argon has a high sputter yield. Also, it is chemically inert, non-toxic, and is relatively inexpensive and cheap as compared to other noble gases like krypton and xenon. On the other hand, oxygen gas is known to react chemically with metals, forming metal oxides easily. Therefore, Argon and oxygen gases are used in the deposition of metal and metal oxide thin films respectively.
The first type of sputtering is radio frequency or RF sputtering. The figure given on the next slide shows the basic schematic of a RF sputtering system. In RF sputtering, an alternating potential of radio frequency is applied at the target, due to which electron exhibits to and fro motion and undergo repeated collisions with the gas atoms near the target surface, which is further used to neutralize surface charges periodically with plasma electrons, which have a higher mobility than the positive ions. Typically, a 13.56 MHz power supply with 1 kilowatt to 3 kilowatt power and about 2 kilowatt peak-to-peak voltage is used to couple cathode through a matching network. There is an acceleration of positive ions from the plasma towards the surface of the target. Due to this bias potential, and atoms are sputtered out due to the transfer of energy from them onto the target atoms. At this high frequency alternating electric field, the relatively heavier ions in the plasma cannot keep a track with the changing field anymore. Thus, only a positive charge could accumulate on the target surface during the half cycles when target behaves as a cathode. The high mobility of electron causes a higher electron current in the plasma as compared to the current due to ion, resulting in a fixed negative bias on target with respect to the plasma. This bias potential is roughly half the value of peak-to-peak RF voltage on the target surface. Due to the negative bias on the electrode, the positive ions present in the plasma accelerate towards the target and hit the target surface to sputter out the atoms.
Here, the given figure shows the RF sputtering setup with matching network. You can see the layout of the RF sputtering machine, in which there is a vacuum system which creates a vacuum inside the chamber. Inside the chamber, there is a substrate holder. There is a sputtered target out of which the atoms are being injected or the etched out. Then there are reactive gas ions and the reactive gas inlet, which is usually the mixture of argon and oxygen for the deposition of metal oxide thin films. And since it is a RF sputtering, so there is a RF power supply. Now, to keep the target holder cool, there is a inlet and outlet of the water. In RF sputtering, a dark sheath or the thin dark layer can be seen separating the luminous glow of the plasma from the surface of the target. Majority of the applied voltage drops across this sheath. The ionized atoms move randomly in the luminous part of the plasma, and only those which enter the dark sheath are accelerated and bombarded the target surface.
So let us now study the difference between the RF sputtering technique, that is the radio frequency sputtering, versus direct current or DC sputtering technique. RF sputtering is a versatile technique for high rate deposition of semiconductors and insulators. While in DC sputtering, deposition by reactive sputtering is limited to lower rates because of the fact that a small amount of the reactive gas must be used to avoid the formation of an insulating layer at the cathode, which otherwise cannot be sputtered. However, since insulators can be RF sputtered, the technique is ideally suited for high rate reactive sputtering. In both DC and RF sputtering techniques, the deposition rate is quite low because the discharge expands to fill the vacuum chamber, leading to poor ionization efficiency. The heating of substrate due to bombardment of energetic species is also a problem. These problems are overcome by magnetron sputtering, in which the electrons are trapped close to the target surface by strong electric and magnetic fields.
Magnetron sputtering. Now, the above studied DC or RF sputtering rates can be enhanced by using magnetic field. Magnetron sputtering is one of the conventional methods of increasing the ionization efficiency of electrons. Magnetic field increases the efficiency of sputtering or the sputter rate by increasing their path length by applying both parallel and perpendicular magnetic fields to the direction of electric field. Another important advantage is the reduced operating pressure. For example, as low as 0.5 torr of argon pressure, with the 0.5 torr of argon pressure, high sputtering rates can be achieved. The figure given on the next slide shows the typical schematic of the magnetron sputtering system. The given figure shows the schematic layout of a typical magnetron sputtering unit. We can see in the diagram that there are magnets naming S and J. Then again there is a cooling inlet and outlet to keep the target holder cool. Then you can see by the circular lines, shown by the circular lines, the magnetic field between the cathode and the anode. You can see the line of force of magnetic field, the plasma, and how then with the help of a magnetic field the atoms are getting deposited on the substrate. In magnetron sputtering, magnets are located underneath the target electrodes. Here, magnets are used to increase the percentage of electrons that take part in ionization events, increasing probability of electrons striking argon plus ions, increase electron path length, and thus thereby increasing the ionization efficiency significantly. In magnetron sputtering, the secondary B10 electrons that are ejected from the cathode surface follow helical paths around the magnetic field lines, undergoing more ionizing collisions with gas neutrals near the target surface. The magnetic field increases the residence time of the electrons in the plasma and hence increases the probability of ion collisions. You can see this phenomena occurring in the figure given on the previous slide. So, due to the presence of magnetic field, the plasma can well sustained at lower gas pressure and gives a higher deposition rate, and moreover the ionization is confined near the target, thus minimizing the heating of the substrate.
Other advantages of using magnets are: number 1, lower voltage needed to strike and sustain plasma. That is, magnets produce a localized magnetic field due to which electrons move in a curved path or the helical path near the target. Curved paths are longer, which promote more collisions en route. More collisions make more ions, and thus it gets easier to strike the plasma. The second advantage is the controlled uniformity. Electron paths are more curved near the stronger magnetic field. Therefore, more the ions collide with the target in regions of high magnetic field, larger is the number of sputtered target atoms. More magnets near the edge or center make the deposition thicker in that area.
Comparison of RF diode and RF magnetron sputtering. Two sputtering systems. The first one is the RF diode and second one is the RF magnetron sputtering can be used for the deposition of thin films as shown in the figure A and B respectively on the next two slides. Both the system comprises of a spherical and cylindrical deposition vacuum chamber fitted with a turbomolecular pump, which are Pfeiffer made, which is operated at a frequency of 833 Hz and continuously backed by a rotary pump in order to evacuate the chamber for attaining a vacuum of the order of 10 to the power minus 6 to 10 to the power minus 7 torr. Also, a cold cathode gauge is also employed to monitor the sputtering pressure over the range 1 into 10 raised to the power minus 2 torr to 5 into 10 raised to the power 11 torr, which is fitted in the deposition chamber. Inert sputtering gases such as argon, oxygen and nitrogen can be put precisely into the deposition chamber using a mass flow controller in order to raise the pressure of the chamber to a value of the order of 10 to the power minus 2 torr for striking the plasma for reactive sputtering. RF diode sputtering system has one 3-inch diameter and one 4-inch diameter diode electrodes which are mounted on the base plate. This system also has a facility of sideways sputtering by using a 6-inch diameter magnetron electrode. System is electrically connected with RF power supply which can give a maximum power of 1.25 kilowatts to the electrodes. A matching unit which can operate either in auto or manual mode is connected between electrode and target to reduce the reflected power. System also has two pulsed DC power supplies as shown in the figure A given on the next slide. The given figure shows the RF diode sputtering system in which we can clearly see the two RF power supplies and the two pulse DC power supplies. Then there is a gas dosing valve, 1 and 4-inch electrodes for the target, and there is a 6-inch electrode for the target, turbomolecular controller, then the pressure gauge, argon and oxygen MFCs, and the substrate temperature controller. The given figure here shows the RF magnetron sputtering system in which we can see a substrate holder, then the 2-inch target gun and the two 2-inch target guns, gas dosing valve, vent valve, gate valve, matching network. Then there is a turbo pump controller, pressure gauge display, the gas MFCs, that is argon and oxygen MFCs controller, and again the substrate temperature controller. The RF magnetron sputtering system has 1 inch and 2 inch diameter magnetron electrode guns as shown in the figure B given above. The sputtering system has been provided with 3 electrode guns and a substrate holder assembly attached with an inbuilt heater and AC-DC motors, which can be utilized for thin film deposition in confocal, glancing angle deposition, GLAD, and multilayer deposition configurations. Confocal configuration could be used for doping of more than 2 materials. GLAD could be used for nanostructural or columnar growth of thin films, whereas multilayer configuration could be used for depositing 2 or more materials in multilayer thin film. In order to obtain uniform thin film, substrate of different sizes 1 cm to 2.54 cm diameter can be used on the substrate holder, and also the distance between the target to substrate can be varied from 2 cm to 7 cm. The substrate holder or assembly is fitted with a heater which is controlled by PID for obtaining substrate temperature up to 850 degrees Celsius. The maximum RF supply which can be applied to the magnetron electrode is of 100 watt using a water cooled RF power supply. To match the impedances and to keep the reflected power at 0, a matching unit is used which can operate either in auto or manual mode and is connected between the RF power supply and target electrode. Then a DC supply can also be used with the sputtering system. The magnetron and RF supply are connected to the water cooling system having circulated chilled water at the temperature of 10 degrees Celsius to dissipate the heat generated during sputtering process.
So students, let us summarize what we have learned in this module. First of all, we have learned about the underlying principle of sputtering technique. Secondly, we learned the mechanism of sputtering in detail. Thirdly, we saw the different types of sputtering, that is the radio frequency, direct current, and magnetron sputtering. Then we saw the difference between the RF sputtering and the DC sputtering. Thank you.